In triangular numbers and sequences, we're going back to the premise of fractals in that you have a geometric representation of repeated patterns. And so in this case, we're talking about items that make an equilateral triangle. That's why it's called a triangular number. The definition is right here, but let's go ahead and take a look at the picture and really look at the definition here. When I have the notation for a triangular number, I have the capital letter T, which represents that it's a triangular number. And then the 1, which is my subscript, tells me how many dots I have in the base. And then what it equals is my total number of dots. So for this first one, I have a base of 1. There's only 1 dot there. And my total number of dots is also 1. Let's look at T2. T2 means that I have a base of 2 dots. The sides are also made of 2 dots, right? So that's where we have our equilateral triangle. But the sum total of all of our dots is 3. When we look at T3, we can see the pattern a little bit more clearly. The 3 represents our base number of dots, or again, you can look at it from each side, that you have a base of 3. When you add up all of the dots in that configuration, you get the value of 6. So let's go ahead, given that pattern that we have, and we want to draw the 4th triangular number and then find its total. So I'm going to ask you to go ahead and pause this video and draw it out on your paper and then come back and we'll check it together. Okay, let's take a look. We're going to go ahead and see that I'm going to start with those 3 dots that I had in the second one, and then the base of 3 that I had up here, right? So I'm looking at this one, that's my T3, and to have T4, I'm going to add 1 more row to it. So that row is going to do 2 things. It's going to give us a base of 4. So I now have 4 as my base, but I want to double check it and make sure each side also has 4 so that I know I drew it symmetrically. So my T4, if I count all the dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I have a total of 10 for T4. All right. Following this pattern, list the next 2 triangular numbers, T5 and T6, and draw those images if we need to. Well, I don't mind drawing images, but what I like to do is look for patterns. That's what all these sequences are about. So let's go ahead and write the first 4 and see if we can come up with some kind of a pattern. So I'm going to list T1, T2, T3, T4, and I'm going to put down T5 and T6 and see if we can't come up with an answer there. So when I look, well, let me put the numbers in first. T1 is 1, T2 is 3, T3 is 6, and T4 is 10, right? So it's not really an exponential growth. There's nothing that's multiplied by my initial numbers that will get me to where I'm going. So let's take a look at what differences we have. Between 1 and 3, I'm adding 2. So I start with 1, I add 2, I get to 3. From 3 to 6, I'm adding 3. From 6 to 10, I'm adding 4. Do you see a pattern emerging? We're going to write about that pattern down here. So if you want to, go ahead and talk about this pattern. But I see a trend happening, which makes me think that from T4 to T5, I'm going to continue this trend and go from +4 to +5. And then on to T6 with +6. So let's go ahead and give that a try. And later on, we'll check it with our formula. So if I take 10 and I add 5, I get 15. So I'm going to hypothesize that my T5 is 15, assuming it follows this trend. If I take 15 and I add 6, I end up with 21. So that is my theory for T6. Okay, the other thing to look at is when you add two consecutive triangular numbers, what are the special numbers that you get? Well, first, let me make a comment that these numbers are found already on the Pascal's triangle. So I'm going to put a little note here. Can find triangular numbers on the third diagonal of the Pascal triangle. We looked at that the other day, and if you're not sure, go on back to the Pascal's triangle video and take a look, fast forward to where we talk about that. So when we talk about consecutive numbers, we're talking about numbers that are right next to each other. So as I'm looking at T1 and T2, if I add those two numbers together, right, 1 plus 3, I get 4. And if I take a look at the next two consecutive, T2 and T3, that would be 3 plus 6, and that equals 9. Looking at the next group, 6 plus 10 gives me 16. Now, we talked about this a little bit with our Pascal's triangle. We saw the same trend happening. And what we find is that there is something very special about all of those numbers that they have in common. Each of them are what we call a perfect square. Each is a perfect square, meaning that if I take that 4 and put it under the square root, I get a whole number out in return. If I take 9 and the square root of it, I end up with 3. If I take the square root of 16, I end up with 4. So all of these numbers, 4, 9, and 16, if you keep going, it would be 25, right? 10 plus 15 gives us the 25. 15 plus 21 gives us 36. Each of them is going to be the next perfect square on the list. So 2 consecutive triangular numbers add to give us perfect squares. All right, so now let's talk about the formula itself. And in this way, we're going to go ahead and use this to check T5 and T6, right? We'll use that as an example. So there's two ways that we can write it, and they both mean the same thing. This one, I have 1/2 ahead of n times n plus 1. It just means I'm taking half of those two things multiplied together. This one multiplies those things together and then divides by 2. Again, both of them mean the same thing. In fact, I could even say 0.5 times n plus 1 is also an option, right? So let's go ahead and use this formula with T5, right? So T5, I'm going to start with a base of 5. So that becomes my n. That value right there is my n value. I plug that in to here. When I have n times n plus 1, it means I multiply it by the number that's in the subscript times the next counting number. So in this case, I would have T5 equals 5 times 6 divided by 2. Because my n is 5, and 6 would be 5 plus 1. So 5 times 6 is 30, divided by 2 gives me 15. And up here, we hypothesized that it would be 15, and we were right. We followed that trend. So we're looking for 21 on T6. So looking at T6, I would have 6 times 7, 42, divided by 2. So 42 divided by 2 is 21. So we're in good shape right there as well. All right, so let's go ahead and look at bringing down that trend so we can see it all together. We have 1, 3, 6, 10, 15, and 21. Those are the ones that we've already found. We're going to look at T7, T8, T9, and T10. Now, when we got T6, what we did was we added 6 to get to T6. So what would I do to T7 if I wanted to do it that way? I would simply add 7. So if I take 21 and I add 7, I end up with 28. If I take 28 and add 8, I end up with 36. If I take 36 and I add 9, I end up with 45. And if I take 45 and add 10, I end up with 55. Well, that's great, but let's go ahead and see if our formula backs up this trend. We know it does. It's shown success, but we want to give you some practice doing those numbers. So T7 would be equal to 7 times 6 divided by 2. So that's 50, let's see here, 28, 7, oh, I apologize. That's not what we want. I'm getting ahead of myself. So 7 times 8 divided by 2, right? We want that n plus 1, not n minus 1. So 7 times 8 gives me 56, divided by 2 gives me 28. T8 is 8 times 9, which is 72 over 2. And half of 72 is going to be 36. T9, that would be 9 times 10, which gives us 90, divided by 2. 90 divided by 2 is 45. And finally, T10 is equal to 10 times 11 divided by 2. That would be 110 divided by 2, which gives us the value of 55. So every single one of these check out. The challenge with doing it this way, when you're adding a number onto the others, this would be the equivalent of recursive. Remember when we did our recursive equations, that was all about knowing what the previous number was. Well, if we know the previous number, we just add what the subscript is to it, and we can get our trend. If we don't know the previous number, we have to use the equations that are up here. These would be considered the explicit version of the equations. So it doesn't matter where it falls on the number line, I'm still able to get a value. Let's take a look at the next page. So here we're going to use our new equations for triangular numbers and find these. So T15 is going to be, actually, before we get started on these, how about you pause this and go ahead and see if you can figure these out on your own, and then come back here and we'll go over them together. Okay, welcome back. T15, let's go ahead and take a look at it. We're going to start with 15, which is our subscript, multiply it by 1 higher, which is 16, divide it by 2. That gives me 240, divide that by 2, and I get 120. So you should have 120 there. T25 would be 25 times 26 divided by 2, and that gives us the number of 325. 400, a little bit larger. We've got 400 times 401 divided by 2 is equal to 80,200. Okay, so all of those can be found using n times n plus 1 divided by 2, or 1/2 n times n plus 1. Okay, so 7 and 8 are a little bit more tricky because it's asking us if it is a triangular number. Here's the challenge. We have an n and another n plus 1 in here, which means if we distribute that and fix it algebraically, we're going to have to end up doing a completing the square, use a quadratic equation to find the number. It's just going to be a hot mess. So I'm going to show you a shortcut on how we can actually find out if a number is a triangular number. Let me get the process written down here first, just so that we all know what we're doing. The first thing is we're going to set the mystery number equal to n times n plus 1 over 2. That's the first thing we're going to do. Then we're going to multiply both sides by 2. And what that does is it gets rid of this 2 in the denominator, and you're left with n times n plus 1. Now, the next part is rough justice. So what I'm going to do is take the square root of the mystery number times 2. So remember how I said multiply both sides by 2? I'm going to take the square root of that result, and then I'm going to use the first digits to the left of decimal to test. Okay? And if we end up with that number, that we know we're in good shape. So let's give this a shot. So I'm going to set this up. I want to know if 1,000 is a triangular number. So 1,000 equals n times n plus 1 over 2. I want to multiply both sides by 2. So now I'm on this second bullet, right? The 2's cancel out on this side. So now I'm left with 2,000 equals n times n plus 1. All right, here's where it gets kind of crazy. I'm going to take the square root of 2,000. And when I take the square root of 2,000, I end up with 44.72. Now, if you have difficulty getting this on your calculator, go to Mode and make sure that you are in Classic at the bottom and not Math Print. If you are in Math Print, it will just give it to you as a square root number. It will not do it to a decimal. You really do need the decimal. So now I'm going to look at this number 44, and I'm going to test that. So my test looks like this. 44 times 45 divided by 2 equals. So when I run that, I get 990. That falls short of the 1,000 that I need. So I might still not be sure. I'm going to go up 1 and see if maybe we catch the 1,000. If it's more than 1,000, then that won't be our number. So let's check. I'll do this over here so that we have a little bit of room. If I do 45 times 46 divided by 2, that ends up with a number 1,035. So 990 and 1035 are consecutive triagonal numbers. 1,000 falls between that, but it's not one of those numbers. So no, 1,000 is not a triangular number. Okay, so let's go ahead and look at 210. Go ahead and pause the video and see if you can go through this process on your own, and then rejoin me and we'll do it together. All right, let's do this together. We've got 210 is equal to n times n plus 1 over 2. Multiply both sides by 2. My 2's cancel out on this side, and I'm left with 420 equals n times n plus 1. I'm going to take the square root of 420, and I end up with a number that is 20.49. So 20 is what I'm going to test. So 20 times 21 over 2 gives me the number of, look at that, 210. Is 210 a triangular number? Yes, it is. Okay, so it's just that simple. Now, taking the square root is not really an official mathematical move. It is a shortcut to get you the information that you need. The lesson is not about completing the square. nor using the quadratic equation. So we're using a shortcut to get the information that we need fairly quickly. Okay, so here's monitoring progress. I want you guys to go ahead and go through this on your own and see how you can do. I will go ahead and film this in another film, and we'll go ahead and take a look at problem solving with triangular numbers in a separate video.